In this video, we're going to derive the formula for the sum of a geometric series, the partial sum. So, for example, if we had a series S equals A plus AR plus AR squared plus AR cubed, and we added on terms until we hit AR to the nth. This would be the nth partial sum of our geometric series. And to make this concrete, if we had, say, A equals 2 and R equals 1/2, this could look like S equals 2 plus 2 times 1/2 plus 2 times 1/4 plus 2 times 1/8, on and on and on, maybe up to an nth term, maybe up to infinity. And initially it might seem very difficult. How can you sum an infinite number of things, an infinite number of terms? Well, there is a technique that works so long as your series is convergent. And if we just think about this quickly, if r is more than or equal to 1, or if r is less than or equal to -1, then the nth term, which is this right here, the nth term of our series is going to be greater than 1, or sorry, greater than 0. And this is a problem because, as we know, as n limits to infinity, if this is true, if the nth term is greater than 0, then we know that this implies the sum is divergent, and we won't be able to calculate it. So all of the work that we're doing here is under the caveat that r is greater than -1 and less than 1. But given this, what can we do? Well, let's begin by writing out our partial sum. S of n equals a plus ar squared, plus ar plus ar squared plus, and then on and on and on until we get ar to the nth. And now we're going to perform a trick. We're going to multiply both sides by r, and because of the nature of this series, this is equivalent to shifting this series down. The first term becomes ar becomes ar squared becomes ar cubed, and so on. And we add this on until we get ar to the nth plus ar to the nth plus 1. And now, because these are both equal and because these are convergent, and it's very important that they are convergent. It's very important that they are convergent. But because of this, we can subtract each side from each other, and it makes sense because they're convergent. We're not adding or subtracting infinity, which is good. We subtract both sides from each other, and well, what do we get? We get Sn minus r times Sn equals, well, the a, we get a, right? But then ar cancels out. Ar squared cancels out. All of these terms cancel out, and then except for minus ar to the nth plus 1. This is called a telescoping series right here. Telescoping series, where you can break it down into the first and last terms. And if we just do a little bit of algebra here, we find that Sn times 1 minus r equals a minus ar to the nth plus 1. So if we divide each side by 1 minus r, we find that the nth partial sum equals a, we'll factor the a out, a times 1 minus r to the nth plus 1 divided by 1 minus r. And this is our formula that you so commonly seen, that you're often just given. This is the formula for adding up n terms in this kind of a geometric series. And of course, if you ask here for the limit as n grows to infinity of this new Sn, you will get a times 1 minus r to the nth plus 1 again, divided by 1 minus r. But n goes to infinity, and we had the assumption to make the series convergent, we had the assumption that r is between -1 and 1. So r to the n plus 1, if you have a number less than 1 to a number that grows to infinity, this is always going to equal 0. And here, so we have r to the n plus 1 as n goes to infinity going to 0. So we will have in our final answer that as n goes to infinity, s of n will equal a times 1 minus 0 is just 1, divided by 1 minus r. So these are the two main formulas that you will see regarding geometric series. And I hope it makes sense how you can use this trick of multiplying by r to shift the series, and because you know it's convergent, subtract them from one another to find not only the finite partial sum, but also the infinite sum as we limit n to infinity.